In section 7.3, we look at simplifying and combining radical expressions. And this can be one of the more challenging sections in this chapter. So first of all, a simplified radical is a radical in which each factor of the radicand is to a power that is less than the index of the radical. Okay, so I'll talk more about that one in a minute because that probably doesn't make a whole lot of sense. Second thing, the radicand contains no fractions or negative numbers. So that means inside of the radical, you cannot have a fraction or a negative. And no radicals appear in the denominator of a fraction. Now, there are two rules that we use to simplify radicals. The first rule is that the nth root of a times the nth root of b is equal to the nth root of a times b. Now this rule says you can multiply two radicals together into a single radical as long as they have the same index, or you can take a radical here and you can pull it apart into two separate radicals. What you do just depends on the situation. The second rule is very similar. It says that the nth root of a divided by the nth root of b is the nth root of a divided by b. So this rule is the same as this rule, except that one is for multiplication and one is for division. Now, let's look at number 1 here, and let's see if we can figure out what that means. So suppose I gave you the square root of 20, and I asked you to simplify that radical. Well, first of all, not every radical that you're given needs to be simplified. So the question here is whether or not the square root of 20 is a simplified radical. Well, it turns out the answer is no, it is not simplified. And the reason is because if you take the number 20 and you do its factorization, we know that 20 is 5 times 4, and we know that 4 is 2 times 2. And so we can rewrite the square root of 20 as the square root of 2 squared times 5. And 5 is raised to the first power, right? That's because the prime factorization of 20 is 2 times 2 times 5. So the index of this radical, remember when you have a square root, the index here is a 2. So this is not a simplified radical because we have one of the factors of the radicand, namely this one right here, is raised to a power that is greater than or equal to the index. And it says that each factor of the radicand needs to be raised to a power that is less than the index. Well, 2 here, this power 2, is not less than the index. So what that means is that it can be simplified. And the way we simplify it is we separate it. We take the square root of 2 squared times the square root of 5. And so what I'm doing here is I'm using this property. I'm taking a product and separating it into two radicals. And then the square root of 2 squared is 2. And so we end up getting 2 times the square root of 5. Now, once you get a little more comfortable with this, you probably won't go through all of these steps. What you'll do instead is you'll say right off the bat that the square root of 20 is the square root of 4 times the square root of 5, and you know the square root of 4 is 2. And so this is a much quicker way to get to the same result. But that's what we mean when we say each factor of the radicand is raised to a power that is less than the index of the radical. It basically means that the radicand, which remember is just the inside of the radical, is as small as possible. Okay, let's do some more examples. So in example number 1 here, we just want to simplify the radical. We have the square root of 48. And so to do this, I am going to think of 48 as the product of two numbers. Now, there are lots of numbers that we can multiply to get 48, but what I want is one of those numbers needs to be a perfect square. And we want to try to pick the largest perfect square that we can. So just brainstorming down below here, we know that 48 is 4 times 12, and we know that 4 is a perfect square. But 48 is also 16 times 3. And out of these two possibilities, this is the better possibility. So we're not just looking for the perfect square factor of the number, we're looking for the largest perfect square factor of the number. And so if we break this apart into the square root of 16 times the square root of 3, we can then go ahead and take the square root of 16, which is 4, and then times radical 3. And so the square root of 48 is 4 times the square root of 3. And so notice that we took our radicand, which used to be 48, and we made it as small as possible. In our second example, you have to be really careful here because in this problem we're looking at the cube root. So when you're thinking about breaking this apart into the product of two radicals, you need to think of perfect cubes. And so we need to break this apart into the product of a cube root times a cube root. And now we have to take the number 54 and think about what factor of 54 is a perfect cube. Well, let's just brainstorm here. You probably know that 54 is 9 times 6, but this choice is no good. And the reason this is no good is because 9 is not a perfect cube. So this is not going to work. But we also know that 54 is 27 times 2. And 27 is a perfect cube. And so we can break apart this radical into the cube root of 27 times the cube root of 2. And then we can finish it by going ahead and taking the cube root of 27, which we know is 3, and then multiply that by the cube root of 2. And so 3 times the cube root of 2 is the simplified form of the cube root of 54. All right, moving on to our next example, we would like to simplify the fourth root of 96. And the higher the index, the harder it is to do because many of us are not real familiar with fourth powers. So it's quite possible that what you'll need to do when you're breaking this down, remember you're looking for a fourth root times a fourth root. And what we need here is we need a perfect fourth power here. And you may not know what number divides into 96 that is also a perfect fourth power. So it's entirely possible that what you'll have to do here is make a factor tree for the number. So what do we multiply to get 96? Well, there's lots of things that we can multiply to get 96. If you're not sure what to do, then just divide it by 2. It's an even number. And so we know that 96 will be 2 times 48. And then we have to break down 48. Well, what can we multiply to get 48? And it doesn't matter what you choose. Eventually, you'll get to the same point no matter what. And so 48 is 4 times 12. And 4 is 2 times 2. And 12 is 2 times 6. And 6 is 2 times 3. So it doesn't matter how you create this factor tree, but in the end, you're going to take all the prime factors of 96, and we can see that 96 is equal to 2 times 2 times 2 times 2 times 2 times 3. So there are 1, 2, 3, 4, 5 factors of 2 times 3. Now, we're looking for a perfect fourth power. So right here, when you multiply 4 2's together, that gives you a perfect fourth power. That is 16. And then what is left over there, 2 times 3, that's 6. And so the factorization of 96 that works for us is 16 times 6. And again, it's because 16 is a perfect fourth power. So now what that means, we can come back up to our problem. The fourth root of 96 is the fourth root of 16 times the fourth root of 6. And now we can finish it because the fourth root of 16 is 2. And so we get 2 times the fourth root of 6. And that's considered to be a simplified radical because we made 96 as small as possible. This takes a lot of practice, but once you get good at doing this, it's not as difficult as it might seem right now. Okay, moving on, we're going to introduce variables into these expressions. And so for these problems, we want to simplify the following radicals, and we're going to say that all variables represent positive numbers. And sometimes you will see this in the homework. Let's talk about what that means very quickly here. If x is positive, then what is the square root of x squared? Well, you all should know that the square root of x squared is the absolute value of x. Remember, you have to have absolute value. But if x is positive, that means x is already a positive number, and so the absolute values become unnecessary. And so anytime you see that variables represent positive numbers, what it means is that if you ever take an even root of the same even power, you don't have to put the absolute value symbols. And so it's more of a convenience thing than anything else. So when I'm trying to simplify the square root of 45x squared, once again, I'm breaking this down into a square root times a square root, and in the first square root, I want a perfect square. Well, 45 is 9 times 5, and I'm choosing 9 because 9 is a perfect square. Now, what about x squared? Well, x squared itself is a perfect square. So we're going to put the x squared with the 9. And so this becomes the square root of 9x squared can be broken down into the square root of 9 times the square root of x squared, and then times the square root of 5. And you all know the square root of 9 is 3. The square root of x squared is x because variables represent positive numbers, and then we have the square root of 5. And so the simplified version of this radical is 3x radical 5. In the second example, it's very similar. We have the square root of 80, x squared, y to the 5th. And so what we need to do here is break this down into the product of two radicals. We're going to want our perfect square in here. And then the other radical, by the way, is what I sometimes call the leftovers. Okay? So what do you multiply to get 80? Well, let's go down here. You all know that 80 is 8 times 10. The problem is neither 8 nor 10 is a perfect square. So this is not going to help us. However, 80 is also 16 times 5. And this is good because 16 is a perfect square. So for the number 80, I'm going to have 16 times 5. For the x squared is a perfect square, so we'll put that in here with the 16. Now, y to the fifth is not a perfect square because it's an odd power. Y to the fifth is y multiplied by itself 5 times. So y times y is a perfect square, and y times y here is a perfect square. And so what we have is y to the fourth times y to the 1. So the y to the fourth is a perfect square, and y to the 1 is what is left over after we pull out 4 factors of y. So now essentially what we're doing here is we're taking the square root of 16, the square root of x squared, the square root of y to the fourth, and then times the square root of 5y. Each one of these simplifies because they are all perfect squares. So we know the square root of 16 is 4. The square root of x squared is normally the absolute value of x, but x is a positive number, and so it's just x. And the square root of y to the fourth is y squared, right? Because y squared squared equals y to the fourth. And then we have radical 5y left over. And this is our simplified radical. Okay, so for the next example, it's very similar, except that you need to be careful because now we're looking at a cube root. So we need perfect cubes, okay? So perfect cubes are from something multiplied by itself 3 times. So obviously x cubed is a perfect cube, okay? But so is x to the 6th, because x to the 6th would be x squared cubed, okay? X to the 9th would also be a perfect cube because that's x cubed cubed. And so is x to the 12th. That's x to the 4th cubed. And so basically, anytime you have a power that is a multiple of 3, that's always going to be some kind of a perfect cube. So when you're looking at simplifying this, x to the 9th is itself a perfect cube. Y to the 7th is not. But we know that y to the 6th would be a perfect cube. And we know that y to the 7th has a y to the 6th power in it. So we're going to break this down, but thinking about perfect cubes. So it's going to be the cube root of something times the cube root of whatever's left over. And again, in here, we're thinking perfect cube. Well, first let's start with the number 80 itself. Now we had just mentioned a minute ago that 80 is 8 times 10. And this is actually good for this problem because 8 is a perfect cube. It's 2 to the 3rd power. So when I break this down, 80 is going to be 8 times 10. X to the 9th is a perfect cube, so the whole thing goes in there. And then y to the 7th is the same as y to the 6th times y to the 1. And y to the 6th is a perfect cube. So we're going to put y to the 6 in here, and then y to the 1 left over. So now all we have to do is simplify. The cube root of 8 is 2. The cube root of x to the 9th is x to the 3rd. And the cube root of y to the 6th is y squared. And there's a little trick for powers. When you have a variable raised to a power, all you have to do is take the index and divide it into that power. And so for that, we get the cube root of 8 is 2. The cube root of x to the 9th is x to the 3rd. The cube root of y to the 6th is y squared. And then we multiply that by the cube root of 10y. And that is our simplified radical. Okay, so moving on to our next set of examples. Once again, we are going to say all variables represent positive numbers. And again, that just means that you don't have to worry about taking any absolute values. Now we're moving on to a different problem. The problem here is that we have a fraction inside of a radical. And that was one of the things that you can't have when you have a simplified radical. So the way we can simplify when we have a fraction inside of the radical is we can separate this into the square root of the top over the square root of the bottom. And this is our rule number 2 that we had on the first page. And then we can go ahead and take the square root of 25 in the denominator, which is 5, and then radical 17 in the numerator. And this is a simplified radical. It satisfies all the conditions. We have no radical in the denominator. We have no fraction inside the radical. And radical 17 is as small as possible. So for our second problem, it's the same thing, but now we have a 5th root. So we can go ahead and take the 5th root of the numerator over the 5th root of the denominator. Now with 5th roots, it's always a little bit more challenging because we're not as familiar with 5th roots. But let me go ahead and break this down. So in the numerator, we're going to break this down into the 5th root of something times the 5th root of something else. And x to the 10th is a perfect 5th power because the power here is a multiple of 5. And so we can say we have the 5th root of x to the 10th. And then 7 is not a perfect 5th power, so we'll just put that down as our leftovers. And then 32, it is true, in fact, that 2 to the 5th power is 32. So you can think of the 5th root of 32 as the 5th root of 2 to the 5th. Or you can just say the 5th root of 32 is 2. Either way, the denominator becomes 2. And in the numerator, the 5th root of x to the 10th is x squared. So the trick there is 5 goes into 10 2 times. And then, of course, the 5th root of 7 is just the 5th root of 7. And so I know this answer doesn't look very nice, but it is considered to be the simplified answer. Okay, and the next problem, it's very similar, except that the radical has already been separated. Now, there's actually 2 techniques for doing a problem like this, but notice that the factors in the denominator both divide into the factors in the numerator. So in this particular situation, it actually makes a lot of sense to put these 2 radicals back together as a single radical. And the reason for that is because now we can divide 72 by 2, which is 36, and x to the 5th divided by x is x to the 4th. And so sometimes you get lucky like this. And then all we have to do next is take the square root of 36 and the square root of x to the 4th, both of which are perfect squares. And so, some problems are nice. They just work themselves out nicely. And other problems, like the previous example, aren't very nice. So it's tough because you really can't judge a problem by what it looks like. You have to just go through and do it. Okay, so the next concept is to simplify a radical expression by combining like radicals. Now, like radicals are radicals that are alike, meaning that they have the same index and the same radicand. So, in other words, the radical has to look exactly the same. So if I have 15 radical 3 minus 4 radical 3, this is like having 15x minus 4x, where x is radical 3. And you all know that 15x minus 4x is 11x. So along that same line of reasoning, 15 radical 3 minus 4 radical 3 would simply be 11 radical 3. So you can combine like radicals by simply adding or subtracting the number in front of the like radical. Okay, so that's a pretty simple example. Let's try one that's a little bit more complicated. Notice in the next example, none of these radicals are alike because they all have different radicands. Even though they're all square roots, they have different numbers on the inside of the square root. So we cannot combine these radicals together. However, we can simplify each one. So the square root of 72 would be the square root of 36 times the square root of 2, which would be 6 radical 2. Then we have plus 3 radical 18 would be 3 radical 9 times radical 2. And that's going to be 3 times 3 radical 2, which is actually 9 radical 2. And then finally we have minus 4 times radical 50. Radical 50 is radical 25 times radical 2. And this is 4 times 5 times radical 2. And so we get minus 20 radical 2. So I have simplified the radical expressions as much as possible. Now notice all of the radicals are alike. We have a radical 2 here, a radical 2 here, and a radical 2 here. So we can combine all these together by simply combining the numbers in front. So 6 plus 9 is 15. So you want me to show my steps here? When I combine those two together, that gives us 15 radical 2. But then we're subtracting 20 radical 2. And 15 take away 20 is negative 5. And so our final answer here is negative 5 radical 2. So to combine radicals, they have to be alike, and you can combine them by adding or subtracting the numbers in front of the radicals. Moving on to section 7.4, this deals with multiplying and dividing radicals, and it really is more of a continuation of the last section. So to multiply radicals together, we already know that we can multiply two radicals together as long as they have the same index. So for example, if you have the square root of 5 times the square root of 15, you know that you can multiply these as the square root of 5 times 15. And the square root of 5 times 15 would be the square root of 75. Okay, so pretty easy to multiply those together. However, the square root of 75 is not simplified because we can refactor it as the square root of 25 times the square root of 3. And the square root of 25 is a perfect square. And so that gives us 5 times the square root of 3. In our second problem, we have the cube root of 9 times the cube root of 21. So we know that we can combine these together as the cube root of 9 times 21. And so if we multiply 9 and 21 together, we get the cube root of 189. But then we can refactor 189 as 27 times 7. Now why am I doing that? Well, because the cube root of 27 is 3. And so we can break that apart and we end up with 3 times the cube root of 7. Now, if that's kind of confusing, and I think it probably is for some people, because many of us probably don't know that 189 is 27 times 7. You could actually go back to the beginning here where you multiplied these together. And as an alternative way of thinking about this, when you have the cube root of 9 times 21, you can think of that as the cube root of 3 times 3, that gives us 9, times 3 times 7, that gives us 21. And then you can see that you have 3 times 3 times 3, which of course is 27. And so that's another way to see that you have 27 times 7. Okay, so for our next example, we have a radical here multiplied by the difference of two radicals here. And so I hope that when you look at this, you automatically think about distributing, because that is the right thing to do. And so what we have is 5 radical 3 times 4. Then we have minus 5 radical 3 times 2 radical 3. Now, when you're multiplying radicals and non-radicals, you should multiply the non-radicals together. So we can say 5 times 4 is 20. So that gives us 20 radical 3. Minus, and then here we have 5 times 2, which is 10. And then we have the square root of 3 times the square root of 3. That is the square root of 9, because 3 times 3 is 9. And that can be simplified, of course, because we know that the square root of 9 is 3. And so this ends up being 20 radical 3 minus 10 times 3. And that will be 20 radical 3 minus 30. And that is the simplified version. Now, you can take a little bit of a shortcut here because this actually happens very often. So going back to this step, when you have radical 3 times radical 3, basically that's radical 3 squared, which is radical 9, which is 3. And so a shortcut is anytime you have radical A times radical A, that's just going to end up being A every single time. And so, for example, if you have radical 17 times radical 17, that's just going to be 17. And so that's a useful shortcut, because if you know that shortcut, you don't have to take this extra step in between. We could have just said radical 3 times radical 3 is 3. So it's up to you, but I encourage you to take that shortcut. Okay, our next example is very similar, except that now we're looking at the FOIL procedure. So we're going to multiply the same way we multiply two binomials together. And so what we get here is 3 radical 5 times radical 5 minus, and that minus sign comes from here, 3 radical 5 times 2. I'm going to say that that is 2 times 3 radical 5. And then we have positive 4 times radical 5. And finally, positive 4 times negative 2 is negative 8. So now we just need to simplify carefully. So we just talked about this. Square root of 5 times square root of 5 is 5. So this is 3 times 5, which of course is 15, minus, here we have 2 times 3, which is 6, radical 5, and then plus 4 radical 5, and minus 8. Now we can combine. 15 minus 8 is 7, and negative 6 radical 5 added to 4 radical 5 is negative 2 radical 5. Now, it's important that you know when to stop. you cannot combine 7 and negative 2 radical 5. For some students, it's tempting to subtract these two numbers, but again, you have two terms here, and these are not like terms because there's no radical 5 attached to the 7. So this is where we need to stop. Okay, so for our next problem, we're going to, once again, FOIL. So this is going to give us radical x times radical x. And then we have plus radical x times radical 2y. And then minus radical 2y times x. And I'm going to write that as minus radical x times radical 2y. And then finally, negative radical 2y times positive radical 2y will be negative radical 2y times radical 2y. Okay, so I know this looks horrible, but it's going to simplify really nicely. Radical x times radical x, well, that's x, isn't it? And then what you have next here is radical x times radical 2y, which is radical 2xy. And then we have minus radical x times radical 2y, which is radical 2xy. And finally, radical 2y times radical 2y is 2y. And then what's really nice about this is these terms cancel out because they're opposites of each other. And so what we get in the end here is x minus 2y. And this is a pretty special problem because in the result here, you can see there are no radicals. And that's not a coincidence. Even though there were lots of radicals in the beginning, we simplified it to a form that has no radicals. And that's because these two expressions in the beginning that we're multiplying together, those are called conjugates of each other. So let me just write this down. If I have radical A minus radical B and radical A plus radical B, the only difference between these two expressions is the sign in between them. And in this situation, these are called conjugates. And the thing about conjugates is when you multiply them together, the radicals always end up going away. This is important because we'll be using this in the examples ahead. Okay, a couple more here. So next we want to do radical 2x minus 5, quantity squared. So remember, when you square something, it means you take that thing and you multiply it by itself. And just a point of clarification here, these are not conjugates, right? Like we just talked about. Conjugates have to have opposite signs. These have the same sign. So when you multiply these, you get square root of 2x times square root of 2x, and then minus 5 times the square root of 2x. That's this one times this one. And then you get minus 5 times square root of 2x again. And finally, negative 5 times negative 5 is positive 25. Now, radical 2x times radical 2x is 2x. Negative 5 radical 2x and negative 5 radical 2x is negative 10 radical 2x. And then finally, plus 25. And I know it's really tempting to want to add some of this together to simplify it some more, but there actually are no like terms left over here. So this is our final answer. Now, number 7 is a little bit different. So notice that both of these problems involve squaring something, but here we have two terms. You have a subtraction symbol here. This is multiplication. When you have multiplication, we actually have a property of radical, or of exponents rather, that say that we can square that and we can square that. Okay, you cannot do that here. Here you must write these out because, again, you have either addition or subtraction. But if it's multiplication, we can simply square the 3 and square the radical 7. Well, 3 squared you know is 9, and radical 7 squared is radical 7 times radical 7, which is 7. And so this is 9 times 7, which is 63. Okay, our last page. This is a long section, I know. So how do we rationalize the denominator? First of all, what does that mean to rationalize the denominator? It means that we want to get rid of the radical in the denominator. Now, when you look at this problem, you might say, well, I don't see a radical in the denominator. And that's actually correct. But we do have a fraction inside of the radical, and that's not allowed. So we're going to break this apart as radical 5 over radical 11. But when we do that, we now have a radical in the denominator. And 11 is not a perfect square, so this doesn't go away easily. So in this case, we have to employ a little trick here. We have to multiply the top and bottom of this radical by radical 11. And the idea when you do that is that in the numerator, radical 5 times radical 11 is radical 55. And then in the denominator, radical 11 times radical 11 is 11. And so this is the simplified radical because, again, all the conditions are met. Notice that we have no fraction inside of our radical. We have no radical in the denominator. And 55 is actually as small as possible. There are no factors of 55 that are perfect squares, and so we cannot simplify this. So this is the simplified radical. Okay, in the next problem, it's very similar. So we have 8 over radical 6. We are not allowed to have a radical in the denominator. So we are going to employ the trick of multiplying by radical 6 to the top and the bottom. And when we do that, on top we get 8 times radical 6. And in the bottom, radical 6 times radical 6 is 6. And so it's very similar to the last problem. However, there's one additional step that we can take here. 8 and 6 have a common factor. And so we can cancel that common factor, which is 2. And what we'll have left over here is 4 and 3. And so this ends up being 4 radical 6 over 3. Okay, for our next example, it's similar once again. Notice that we have a radical in the denominator. That's no good. Now you could just multiply the top and bottom by that radical like we did here, but this is a pretty complicated radical. So instead of doing that, what I'm going to do is I'm actually going to combine these radicals together into a single radical. Now, why am I doing that? Why would I want to do that? Well, the answer is because we have common factors here that could be canceled. So you know 5 goes into 10 twice, and you know x squared cancels 2 of those x's. And so what you have left over when you do the simplification is you have a 1 on top, and you have 2x in the bottom. Now we can re-separate this as the square root of 1 over the square root of 2x. And of course, the square root of 1 is 1, and so we have 1 over radical 2x. And now notice that this expression here is much simpler than the original expression. And so we can now multiply by radical 2x to the top and the bottom. And 1 times radical 2x is radical 2x. And radical 2x times radical 2x is 2x. And so I know it may not look like much of an improvement, but this satisfies all the conditions of a simplified radical. We have no radical in the denominator, we have no fraction inside the radical, and 2x is as small as we can make it. Okay, our last example. Again, I know this is a long section. We want to rationalize the denominator. We cannot have these radicals down here, but we have a minus sign. So we have to employ the trick, which is to multiply by the conjugate of the denominator. And the conjugate is radical 7 plus radical 5. Okay, so this is the conjugate. Now, it's coincidental that this is the same as this. You would multiply by this here no matter what you have up here. But whatever you do to the bottom, you got to do the same thing to the top. So now we have to multiply these out, and this is going to be a lot of work. So what we get, big fraction. In the numerator, we have radical 7 times radical 7. And then we have plus radical 7 times radical 5. And then we have radical 5 times radical 7. And finally, radical 5 times radical 5. That's the numerator. The denominator is very similar. Radical 7 times radical 7 plus radical 7 times radical 5 minus radical 5 times radical 7 and minus radical 5 times radical 5. So now you have to very carefully simplify. Radical 7 times radical 7 is 7, so both of these are 7. Radical 5 times radical 5 is 5, so both of these are going to be 5. And radical 7 times radical 5 is radical 35, and that actually occurs here, 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 and here. And so when we simplify all those, we get 7 plus radical 35 plus radical 35 plus 5 over 7 plus radical 35 minus radical 35 minus 5. Okay, so now we're going to simplify the numerator. Well, 7 plus 5 is 12. And radical 35 plus radical 35 is positive 2 radical 35. In the denominator, it's a little bit nicer. Radical 35 minus radical 35 cancels out, and 7 minus 5 is 2. And then one final step here is we can cancel this 2 with the 12, which gives us 6, and with this 2, which gives us 1. And so our final answer here is 6 plus 1 radical 35, which is, of course, just radical 35. Okay, so if you made it all the way to the end of this video, congratulations. It's a long one. This is going to take a lot of work to master this material, so you have to get practice. You will get frustrated, I think, from time to time working on these problems, but there's really no substitute for just doing lots of examples, and sooner or later you start to get the hang of it, and it just becomes a part of you. So good luck.